Today we're happy to have Slava Rychkov to tell us about interacting fixed point without conformal invariance. Thank you.
Okay, great. Today, after Monday's talk, there's going to be something more informal. So I'm going to tell you about this work I did with Jimenez-Grau, who is a postdoc at IHES, and Yuna Kayama. I want today to discuss question of why we normally at normalization group fixed points have conformal invariance and why sometimes we don't. So actually we had a discussion during lunch today about whether this fact that we do have conformal invariance is how certain we are about this fact. And I just would like to reiterate that from my perspective, the fact that you can compute critical exponents of, say, the three-dimensional easy model using the conformal bootstrap, as I was describing on Monday, and then these critical exponents agree with experiments, with Monte Carlo simulations, with whatnot. For me, it's an indirect evidence that we are not fooling ourselves, that really the fixed point is conformally invariant. So we are certain about it. So now I would like to just gain some theoretical understanding why this is the case. And probably you have seen some discussions of this in textbooks, and you probably remember from the discussions that the question of scale without conformal invariance, scale and conformal invariance, it's usually phrased in terms of properties of the local stress tensor plane. So for the theory to be scale invariant and conformal invariant, the trace of the stress tensor operator has to have some special properties. And maybe you recall from your studies of, say, two-dimensional conformal theory that usually the property that people impose that the trace of the stress tensor has to be zero. So in fact, in many textbooks, you will encounter a statement that this property is a consequence of scale invariance. And then once you have this property, then in addition to scale invariance, you also acquire conformal invariance. So in fact, this statement, even though it occurs in textbooks, is actually not correct. So let me give you a more correct statement. So correct statement is that for scale invariance, the property that you are supposed to have is that the trace of the stress tensor is not necessarily equal to zero. This is just a partial case, but a property which would be sufficient is that the trace of the stress tensor is a divergence of some vector of rate. This operator is called virial current. So if this property holds, which is more general than this one, then the theory is going to be scale invariant. And I hope so that this is rather clear, but let me give you an argument. Let me give you a quick argument why this is the case. You can give the argument by thinking about what happens if the theory undergoes a scale transformation. So a scale transformation would mean rescaling the coordinates by some small parameter epsilon. And when you do such a rescaling, then the metric, so you suppose that you're in flat space, you do a rescaling, and the metric changes by some constant times the original metric. So scale transformation just rescales the metric by a constant factor. And as we know, when you do some change of the metric to the system, then the action of the field theory, it changes by the integral of the change of the metric times the stress tensor. This is the usual formula. So now, if the stress tensor is traceless and if the change of the metric is proportional to G mu, then this is equal to 0. So I'm working actually in flat space, so the original metric is flat. So this shows that yeah, it's 0 if t mu is equal to 0. If on the other hand, if t mu is a total divergence, then of course, then this integral is 0 as an integral of a total divergence. So it's also 0. So this simple argument. Okay, it's not 100% rigorous, but it kind of explains why having the stress tensor to be a total divergence is a sufficient condition for scale invariance. So now, what about conformal invariance? So for the conformal invariance, you have to consider transformations of space-time coordinates, which are not just rescalings, but for conformal invariance, you're supposed to consider transformations of the form x mu goes into x mu plus epsilon c mu, where x mu is one of the conformal vector fields. So scale transformation is one of these vector fields, but there are, of course, also rotations, translations, and there is a special conformal transformation vector field that I mentioned on Monday, which was first discussed by Castro. And so this actually is special. I'm only going to write down this special conformal transformation vector field because it's the only one which you may not remember. So it has the form 2x mu x times the derivative plus minus x squared d mu. And so the important point of this formula that I would like to point out is that the coefficients of the special conformal vector field, they are of second order in the coordinates, in the space-time coordinates. And so for this reason, the condition for conformal invariance can be written in the following form. Suppose that the trace of the stress tensor, T mu, is equal to the divergence to second derivative. So d lambda d rho of some operator, let me call it L lambda rho. Now, what's going to happen if you have this condition? So again, you apply a conformal transformation, you apply infinitesimal change of the metric. You compute the change in the metric. So the change in the metric, in this more general case, delta G mu, is as usual equal to d mu c mu plus d nu c mu. And the defining condition of the conformal Killing vector field is that this quantity is actually proportional to delta mu times the divergence of the vector. Can you still see here?
No.
So again you have delta mu, but now it's multiplied by this factor, the divergence of the vector field. Now let us plug it into this equation, into the change of the action. What are we going to get? We are going to get the trace times this divergence of psi. And as I said, psi itself is a polynomial of second order in coordinates. So when you take a divergence, you get something which is linear in coordinates. And the trace T mu is a second derivative of something. So when you integrate by parts, you get something which vanishes. And so this implies that delta S is equal to 0. So now you can see what is the difference between scale invariance, which says that you have this virial current, and conformal invariance requires that the virial current itself is a divergence. So if you can write the virial current itself as a divergence, then in addition to scale invariance, you're going to have conformal invariance. So this whole story has been known for a long time. It's actually now what I described here is written in a classic paper by Polchinski in '88. So it's a well-known story, even though it somehow didn't get into textbooks. Now, based on this story, let us ask ourselves the following question. So can you have theories which are scale invariant but not conformally invariant? So for such theories to exist, you have to have in your theory a virial current operator, V lambda. So what should be the properties of this operator? So this operator, it should have the same quantum numbers as the stress tensor. So the stress tensor is a singlet under all global symmetries that you may have. So the virial current should also be a singlet under the global symmetries. Another property, important property of the stress tensor is that it has scaling dimension d if you are in d-dimensional space-time. And so the virial current also should then have dimension d-1. And in addition, this virial current should not be conserved, because if it's conserved, then of course the right-hand side vanishes. Then we have a simple case. So the theory is conformally invariant. So now you can ask yourself, well, how likely it is that in a theory you are going to have a current operator which has dimension d-1, and yet it is not conserved? Well, you may think that this is not very likely, at least if your theory is interacting. Because if your theory is free, maybe this can happen. This operator may just be there for some weird reason. But if your theory has interactions, then operators acquire some anomalous dimensions. And we know that generically, if current is not conserved, then it's going to acquire some anomalous dimension, and then it's not a virial current candidate. It just cannot appear in this right-hand side because it doesn't have the right scaling dimension to appear there. And so if you take this point of view, then you may be led to conclude that interacting quantum field theories, which are scale invariant, they are necessarily conformally invariant. For free theories, this doesn't have to be the case. In fact, there are free theories which are scale but not conformal. So let me give you a classic example of a free theory, which is scale without conformal. So the classic example of this is theory of elasticity. And what does it mean, theory of elasticity? So you have some medium, and in the medium you have a vector field which tells you the deformation of this medium. We are in Euclidean, and you write an action which is just a combination of the leading term in the derivatives that you may write down. So if u mu is your deformation field, then you write an action which is a combination of two terms, T mu u mu squared with some coefficient lambda, and then d mu u nu squared with some other coefficient. So the claim is that this theory is scale without conformal. So let us see why this is the case. Well, first of all, this theory has a virial current candidate because it's a free theory. The field u mu has dimension d minus 2 over 2. If you consider things like u du, it has dimension d minus 1, but it's not necessarily conserved. So in this theory, there is a lot of fields which can play a role of the virial current. That's okay. For free theory, this is allowed. So you can actually do a calculation for the stress tensor in this theory, and you will find that this virial current appears in the trace of the stress tensor. So it is indeed scale without conformal. But there is actually another way. There is an even simpler way to convince yourself very quickly that this theory is scale without conformal, which is to compute the two-point function of the field u mu. Well, you can do an explicit calculation, but without any calculation, you know that this, just from rotation invariance, you know that this two-point function is going to have the form a divided by x squared to the power d minus 2. So this is just from dimensional analysis, no, d minus 2 over 2. And then there's going to be the only structure which is consistent with rotational invariance is a linear combination of this sort of two terms. You can compute everything explicitly in terms of lambda and mu. So b is going to be some function of lambda and mu, some rational function of lambda and mu. But the point is that it's a non-trivial function of lambda and mu. And for the theory to be conformally invariant, if you studied conformal field theory for 1 or 2 hours, then you know that the two-point function of a primary vector field in a conformal field theory has this form with b equal minus 2. So this is a very important tensor structure which appears in conformal field theory because it's a Jacobian over the inversion transformation. And if you just take some generic values of lambda and mu, then this b is not going to be equal to minus 2. It's just going to be some random number. And so you know that this field cannot be a primary vector field.
The choice of lambda and mu where it is minus 2.
So the only choice where it is minus 2
Maxwell.
Yeah, Maxwell.
is well, I wanted to say Maxwell, but then I got a bit confused because so Maxwell theory is conformally invariant in but the field u mu in Maxwell theory is not a gauge invariant field, so you're not supposed to consider its two-point functions. Yeah, so there are some comments to be said about this theory. So first of all, you see that this theory doesn't have gauge invariance, which is okay because I'm working in Euclidean signature. And also this theory is not unitary or not reflection positive in Euclidean signature. So I apologize for particle physicists in the room, but there are going to be a lot of non-unitary theories today. So in fact, this question scale without conformal, it's often studied in presence of unitarity, especially by particle physicists. But in my opinion, this is a little bit of a red herring, because in statistical physics, there are many interesting non-unitary theories, like this one. And most of them, in spite of being non-unitary, they do end up being conformal. So in fact, if you manage to prove a theorem that perhaps scale invariance plus unitarity implies conformal invariance, yeah, you would explain part of the story, but you will definitely not explain the whole story, because there are somehow many theories which do manage to be conformally invariant without being unitary. So there is still something to be understood. Okay, yeah.
How do we see that, like, just checking that is sufficient? Like, that seems like a necessary condition. How do you see that that's also sufficient?
This one?
Yes.
So this is a sufficient condition. for conformal invariance. Because I said that if this is satisfied, then you know you can integrate by parts and things vanish, so you get conformal invariance.
But this would also be true for like statistical mechanical models where like the Hamiltonian is 0 and so on.
Hamiltonian is not 0, but it doesn't change under an infinitesimal conformal transformation, and so the theory is conformally invariant. Only the change of the Hamiltonian vanishes, right? Not the Hamiltonian itself.
So what replaces unitarity in the statistical? Is there any concept which
In statistical physics, unitarity is usually replaced, often is replaced by a requirement to have positive weights, to have non-negative energy. And here, this is true. You know, there are some conditions on lambda and mu under which this is true, which are satisfied in theory of elasticity.
So is it positivity or real valueness?
Usually, if you start relaxing this positivity, then you kind of go in some non-physical regime, in which sometimes people go in statistical physics, like they consider imaginary magnetic field and so on. But the most commonly considered case is really real values.
I always hear people say that unitarity gets mapped to reflection positivity in statistical physics. Is it the same as the condition you're pointing?
No, indeed, this theory it's not reflection positive. This theory is not reflection positive. However, it does have a positive action.
Okay.
So it just shows that positivity of the action and reflection positivity are two different conditions.
I don't want to hammer on this point, but if I arrange the Lamé coefficient to be in this magic ratio, there's 2, and I build this thing and I touch it at 0 temperature, what am I supposed to see? Is that even a meaningful question? Like in terms of response, and it will be a peculiar elastic medium.
It's going to be a peculiar elastic medium because along some direction, it's not going to have any resistance to deformation. So I know you work on very exotic media, so perhaps it's within your means to construct this. Yeah.
Are you primarily discussing Euclidean?
Minus, one of these has a minus.
I'm sorry?
Are you going to primarily discuss Euclidean theories or?
Yeah, I'm going to really discuss only Euclidean theories. Okay, so this was my point of view maybe a few years back, and I was very happy with this point of view that in free theories you can have scale without conformal, but the moment you introduce interactions, all virial currents, they acquire anomalous dimensions, and so you cannot have scale without conformal, you will necessarily have conformal. Unfortunately, this point of view turns out to be wrong. So there are some interesting theories out there which are both interacting and scale without conformal.
Are they also not unitary?
And the examples that I know of are non-unitary also.
You know, any example of like unitary scaling invariant, which is not conformal?
I do, but those are free. The ones that I know of are free. So I would like to explain to you what was wrong in this reasoning, how is this paradox resolved, and what is this new mechanism which allows these theories to escape this reasonably good argument that I gave you. And so the example that led me to change my mind is this model which is called dipolar ferromagnet. It's actually very interesting physical model. So let me maybe explain in words because I'm not sure how many of you care about magnets. Once heard Nimar Kanikamet declare emphatically in front of the audience of theoretical physicists that one of the reasons so he switched from condensed matter to particle physics because one day he woke up and he just said that I realized that I couldn't give a damn about magnets. So ferromagnets, of course, ubiquitous. And one interesting thing that is not appreciated is that we often describe ferromagnets by writing to them an effective Landau-Ginzburg field theory description, which is something like field phi to the fourth field theory. So you may write some field theory of the form d phi squared plus m squared phi squared plus lambda phi to the fourth, where phi is supposed to be a field which represents your magnetization. It can have 1, 2, or 3 components. And it's important to realize that this description is not quite complete, because in the actual ferromagnets, so you have interactions between spins, and this interaction comes from 2 sources. So there is an exchange interaction, quantum mechanical exchange effect interaction, which is short-ranged. And this interaction, it can be viewed as a source, for example, for the short-range kinetic term in this Landau-Ginzburg description. But there is one other effect which is always there. So exchange interaction, it may be there, it may be not there, it may be ferromagnetic, it may be anti-ferromagnetic, so it depends on many things. But there's one effect which is always there, which is the dipolar effect, which basically says that if you have some magnetic moment, local magnetic moment in one point, this magnetic moment is going to create a magnetic field, and this magnetic field is going to act on the magnetic moment in another point. And this effect is always there. And moreover, its strength is universal. It's just figured by the Maxwell equations, unlike the exchange interaction. And so the reason why this is not always discussed in textbooks is that there are sometimes situations when the exchange interaction is much stronger than this dipolar interaction. And so you can neglect it. But it's important to realize that that this neglect can never be precise. So in fact, let us write the form of this. You can work out the form of this dipolar interaction just by coupling your magnetic moments to the magnetic field, which fluctuates, and then integrating it out. Once you do this exercise, you compute the form of this dipolar interaction, and then you get a term which in momentum space is going to look like this. So it's going to be qi by I squared divided by q squared. Now I'm considering 3-component ferromagnet case. And because of this 1 over q squared, which is just because you're integrating out the massless field, the magnetic field, you're generating this singularity. This shows that this term is actually a relevant perturbation of this local action. So no matter how small the coefficient of this term is, if you get sufficiently close to the critical temperature, and this of course is an experimental issue, how close you need to get, you will see the effect of this term. So you can, in terms of renormalization group, what you can think of is that, okay, normally we consider renormalization group flow, which takes you from the Gaussian fixed point, which corresponds to lambda equals 0, to say O3 fixed point, O3 Wilson-Fisher fixed point. And this is the renormalization group flow, which is very well known, very widely studied. However, what I'm saying here is that this flow is an idealization. There's always small amount, small or large, depending on the material, of the dipolar interaction present in your system. And this dipole interaction is going to lead you to another fixed point sooner or later. And this other fixed point is called the dipolar fixed point. And it's been first discussed by Haroni Fischer in '73, by author Haroni's father and Michael Fischer, Amnon Haroni. And so, so in fact, it depends on the materials.
Can it be screened, dipolar interaction in some
Can it be?
screened if you have other, add some degrees of freedom that are charged? Are there situations where it's exactly zero?
It's in ferromagnets. I don't see how it can be streamed. If suppose you have an antiferromagnet, of course, is also described by this sort of actions. But then the dipole interaction is absent, so this effect is not there. In ferromagnets, I think. I don't know. Discuss.
Is there a flow that directly leads from the O3 to the?
Yeah, there is also a flow from here. So you can do computations in this dipolar model if you know anything about the epsilon expansion and how you do compute critical exponents using Feynman diagrams. All this works perfectly well also for the dipolar fixed point, but you have to modify your diagrammatic sensitivity. So in fact, what you can do, what you can observe is that you say, if you are really sitting at the dipolar fixed point, then the effect of this dipolar term is maximally strong. And because it's relevant, and because here in the numerator you see the divergence of phi I, it means that at the dipolar fixed point, you have a constraint that the divergence of the order parameter is equal to 0. So you can do calculations at the dipolar fixed point just by computing using the usual Landau-Ginzburg action with this extra constraint. So basically your propagator is going to be not 1 over p squared, but the transverse form t mu d nu minus p mu p nu over p squared over p squared. You can do the usual diagrams. You can compute anomalous dimensions using Feynman diagrams, and you can do the epsilon expansion. And so this was done in the 70s and the 80s. You find critical exponents. You find that in the epsilon expansion, these critical exponents are different from Wilson-Fisher. You really get different coefficients, which is not surprising. So it's a different, really, universality class. And there's been some experiments that observed this, for example, this suppression of longitudinal fluctuations of order parameter. There are some materials where this dipolar interaction is really strong. And this has been seen experimentally. Okay.
The fixed point has a single O3 symmetry, doesn't have rotation and.
Yeah. So this fixed point, very importantly, at the fixed point, at the usual Wilson-Fisher fixed point, you have a product of two O3s. You have a global O3 times the rotation O3. And at the Wilson-Fisher fixed point, the field phi is a scalar. At the dipolar fixed point, the field phi becomes a vector field. And so O3 global times O3 rotation is broken to a single O3. So the diagonal O3. This is an important feature. So what I want to say, what I want to explain now is that this model is an example of a local quantum field theory, which is interacting and which is scale without conformal.
In what sense is it local?
In the sense that it has a local conserved stress tensor operator. So you may be worried about this constraint that I'm imposing, but in fact, the way to deal with this, I don't want to erase there, so I'm just going to rewrite. So the action, the dipolar action that we can consider is equal to the Wilson-Fisher action, which is written there. And then I'm going to incorporate this constraint. I'm just going to do a trick, incorporating it via Lagrange multiplier. So I'm going to introduce some field U times Ti phi I. And given that I can write it in this local form, you have a stress tensor for the identities. So this for all you know, this is a local field.
For instance, you think it obeys something like crossing symmetry.
Definitely. And so how do you convince yourself that this theory is scale without conformal?
Can you solve this constraint like phi I equal epsilon ijk bj ak?
Well, if you try to do it, you will be introducing some gauge freedom into the game.
Is
And
this a
this is
gauge
not.
theory?
This is not. I don't think this is.
But is this a gauge
In that description, it would be a gauge theory. Yeah.
interacting gauge theory?
But for my purposes, it's not a very useful thing to do. But yeah, I heard of other people who did this sort of tricks and found them useful. Yeah, so first I would like to then, in the rest of my time, I want to first of all explain to you why this is scale-without conformal, what is this virial current, and why the virial current doesn't get renormalized in this theory.
In 3 dimensions.
In 3 or minus epsilon. Let's do it in 3. Yeah, let's do it.
What's the constraint in 4 minus epsilon dimension?
You have to assume, of course, that it has a 4 minus epsilon components. Easy.
How do the indices work in the kinetic term? Gradient terms.
Uh,
F mu.
Here they don't talk to each other. Yeah, so here it's d mu phi I.
And the number of components of phi should be equal
To the number of dimensions. It's a simple theory. You can compute anything you want. And one thing that helps to start the discussion with is the 2-point function of phi. Just like here, I convinced you that the theory of elasticity couldn't be conformally invariant by looking at the 2-point function. Let us try to look at the 2-point function of phi and see whether there is something about it which tells us right away that this cannot be.
So this is a theory of a vector field which is massive and there is no gauge invariance.
Well, no, there's no gauge invariance, but massive, it's massive. Of course, to go to the fixed point, you have to tune mass to get the scale invariant theory. So you tune the bare mass and then you recover a scale invariant theory in the infrared limit.
I'm just worried about things like renormalizability. I guess that is not.
There's no issue. It's renormalizable for all we know. It's a perfectly healthy theory from this point of view. It's not unitary. It's not unitary. So that's why we haven't seen it in particle physics textbooks, but it's a good, as a statistical physics field theory, it's a good theory. So you already see where I'm going. Let me compute the 2-point function of this field phi I. It's a vector field, so the 2-point function is going to have more or less the same structure as here, with some, with some linear combination of this delta mu, and there's going to be a scaling dimension here. So there's going to be a 1 over x squared to the power delta phi, and there's going to be some linear combination of delta mu and some coefficient x mu, sorry, delta ij, xi, xj over x squared. Now we know that the field is conserved. Well, the I phi I is equal to 0. we know, well, I know, but maybe you will believe me, that in a conformal field theory, a conserved vector field has a canonical, have a canonical scaling dimension. So if the theory were conformal, then we should have that delta phi is equal to d minus 1. It has to be really a conserved current in the conformal field theory. It has to have dimension d minus 1. It should be if the theory is conformal. If it's a CFT. But what is the dimension of phi in this theory? It is, as I said, you can do epsilon expansion, you can compute the dimension of delta phi. It starts with d minus 2 over 2, and then it gets some corrections of order epsilon squared in epsilon expansion. Just like in phi to the 4th theory, these corrections have been computed to high order. You can try to resum them. You can see what the dimension is in 3D. But this anomalous dimension is extremely small. Just like in the Wieslund-Fischer theory, the anomalous dimension of phi is extremely small. It's of the order of a few percent. Same here, you only get an order of a few percent correction to the dimension of phi. And in particular, these corrections, they cannot raise the dimension of phi to the dimension of a conserved current. So the phi doesn't have the right dimension to be conserved, to be a conserved current in a CFT.
Sorry, why can't the epsilon expansion just not be a good dimension? We don't have any general reason for expecting setting epsilon to be 1 to give a good answer.
Well, of course, you don't just set epsilon to 1. You have to resum, barrel resum. Yeah. It's not a proof, but it's the physics level. It's not a mathematics proof. But at the physics level, I think the answer is elsewhere. So I think that phi is really has doesn't have the dimension 2 in 3 dimensions. It has much smaller dimension, and we have to understand what's going on. There's a much more natural explanation, I think, because you see, even if the epsilon expansion, you could say, okay, epsilon expansion, maybe you don't know what the behavior. See, not only should it give a very big anomalous dimension, but this anomalous dimension should miraculously, as a sum of all these terms, to sum up to exactly 1/2. No, sorry, is it 1/2? No, 1.5. 1.5 to raise the anomalous dimension from 1.5 to 2. So this is already too much of a quiz. This is just going to be some random number.
Just consider this in d equals 4.
D equals 4 minus epsilon. In d equals 4 minus epsilon, there is already a mismatch here.
Yeah, just consider epsilon equals.
But there it's free. So.
In 4 minus epsilon, it's not free.
Oh yeah, I thought you were saying 4. Yeah, 4 minus epsilon, you have 4 minus epsilon fields.
Yeah. So, yeah. So this is an argument that the theory is not conformal. You try to press on and you say, okay, what is the virial current in this theory? So you do a computation. You compute the stress tensor. You compute the trace of the stress tensor. You discover that yes, there is a virial current. And the virial current has the following form.
Sorry, can you clarify, what is the claimed total symmetry of this model? Besides the O3 and the scale invariance, is there also a shift symmetry?
That's the part you are a little bit stealing my punchline, but yes, there is a shift symmetry. And it's going to play an important role in the explanation of the positive. So the virial current is given by U phi mu. You do a computation, you find that there is this field U phi mu, and you have to explain. So this is a puzzle. We have to explain why this field has dimension d minus 1. In free theory, in the free theory limit in 4D, this is true. Because if you look at the action, U di phi I, you see that the dimensions, the classical dimensions of U and phi I, they do end up to d minus 1.
What's U? So maybe
U, it's that field, Lagrange multiplier field.
This is why it is not unitary.
I'm sorry?
Is it why it is not unitary? Because it has to be I times U.
It's a Lagrange multiplier. I don't say if it's real or.
For convergence.
In fact, unitarity, you don't have to discuss. You see this form of writing the action U di phi I. It's only important if you want to exhibit that the theory has a local description with a stress tensor. If you want to study unitarity, you don't have to look at this form of the action. You can look at the 2-point function of phi already, and you can ask if 2-point function of phi is reflection positive. And you can show that for this dimension of phi that we have, it's not going to be reflection positive. Already the 2-point function of phi, so it has nothing to do with U.
But in order to formulate this theory as a local theory, you need to integrate over U, right?
If you want to define it as a local theory, yes, you need to integrate over U. If you want to study the question of reflection positivity, you can ask this question already in terms of correlation functions of phi. But reflection positivity is defined as a property of correlation functions. You don't need to do the action to check it.
If I solve this constraint and rewrite phi in terms of curl of some gauge field, can I see that theory as local? Is that an argument that it's local?
It could be one of the arguments that it's local.
But is it a valid argument?
For me already this one is valid, but for some people not. Let's pile up a few more arguments to convince ourselves.
So it's a local theory of two form, something like that.
It's just one form, right? It's 3 dimension. Phi I equal epsilon ijk dj ak. Just a gauge field ak.
No, but you see, in locality, it has to be defined, we are doing here, okay, we are massaging Lagrangians, but locality of the theory is a property of the theory independently of its Lagrangian description. For me, locality means the theory is local if it has a local conserved stress tensor operator, which this theory does. So which has well-defined correlation functions and which satisfies void identities with correlation functions of other fields. I think as long as this property is true, I call this theory local, and here this property holds. So, but okay, I just want to explain to you one more remaining thing is why this dimension of V doesn't get renormalized. And so this non-renormalization, we explained it. For us, it was actually the main puzzle to be explained, and we explained it invoking the existence of the shift symmetry. So you see, in this theory, as Clay already noticed, there is this shift symmetry. Which acts on the field U, which shifts the field U by a constant. So it's kind of weird because, of course, there are many theories in physics which have shift symmetries, but the ones that I'm familiar with, most familiar with, they are effective field theories at low energies. While this theory is a scale invariant theory with non-trivial anomalous dimensions, so it was the first time I realized that scale invariant theories may have such shift symmetries. So this was for me a little bit of a surprise. So what are the consequences of this shift symmetry? So first of all, we have this shift symmetry is a local symmetry, meaning that there is a current. There is a conserved current associated with the symmetry, and the current of this symmetry is nothing but phi mu itself. So phi mu is a current of this symmetry. So it's the corresponding current. And in particular, you can also write a shift symmetry charge by integrating the current, or as we usually do by integrating the current over some manifold. You define the charge.
Is this symmetry spontaneously broken?
Well,
So suppose I take this theory of finite mass. Would I get the Goldstone boson in it? Since there is a shift symmetry?
so let me first answer to play. So the theory is spontaneously broken once we're at the fixed point, because the 2.5 because the correlation function of u is equal to 0, while when we shift u when we apply the charge, then we get the uu. When you act with u with a shift charge, you get the unit operator, which is of course not zero. So this shift symmetry is necessarily spontaneously broken, but there is no associated Goldstone boson. And this is only possible because our theory is non-unitary. So in fact, if you consider a 2-point function of u and phi mu at in momentum space, then this 2-point function has a pole, u mu over q squared. And so in a unitary theory, if you have this 2-point function with a pole, then okay, this is the basis of the Goldstone theorem, which says okay, other correlation functions also should have this pole. And all correlation functions have the pole, so there has to be a Goldstone boson. But no, here not. So here this 2-point function has a pole, but the 2-point function uu and the 2-point function phi mu doesn't have 1 over q squared pole, but they have a 1 over q squared with some non-trivial anomalous dimension behavior. So such a thing is only possible in a non-unitary theory, I think, and that's actually one of the reasons why all interacting examples of scale with unconformal known to me, all of these examples, they are based on this mechanism, and all of them are non-unitary. So if you want to construct a unitary example, there has to be some other mechanism. But okay, so we have this shift symmetry. How does it explain that delta E is equal to d-1? So this is interesting. And here, this is based on the notion of shift multiples. So in conformal field theories, we have this very important notion of conformal multiplets. Turns out that in this particular scale-out conformal theory, there are no conformal multiplets, of course, but there are these interesting shift multiplets. So what are these shift multiplets? So you call a shift multiplet a family of operators, let me call them O0, O1, O2, and so on, with the property that, okay, the first operator has to be annihilated by the shift charge. And so the shift charge, by it has negative dimension. So the scaling dimension of the shift charge is equal to minus the dimension of u. So it's negative. Well, it's minus the dimension of u because it maps u to the unit operator as dimension 0. So you have this multiplet of operators of ever increasing dimension, and with the property that if you act with a shift charge on the next operator, you get the previous operator. So in particular, the dimensions within the shift multiplet, they are quantized in units of delta U. So take an operator which is annihilated by the shift symmetry. On top of this operator, you can build a shift multiplet.
What does it mean, operator? State is annihilated. What do you mean by operator being annihilated by?
Well, I mean that I mean that it's shift invariant.
Yes. Commutes.
Yeah, it commutes. Yeah, commutes. So let me give you two examples of the shift multiplet. So the simplest example of shift multiplet is 1 u squared, 1/2 u squared, 1/3 factorial u cube, and so on. So this is a shift multiplet in the free theory. So clearly in the free theory, this is a shift multiplet. Now the claim is that if you turn on interactions, then all these operators are going to get renormalized. They're going to get some, as usual, there's going to be some operator mixing. Once the dust settles, you are going to get a renormalized shift multiplet, which is going to be quantized in units of the renormalized value of delta U. Now, so this is a very trivial example. Let us consider a more interesting example. Is a shift multiplet which is built on top of the field phi I. Why is this interesting? Because the second operator in the shift multiplet is precisely the virial current, U phi I, and then U squared phi I, and so on. So we are almost there. So now from here, I'm going to argue that the virial current is not renormalized. Well, this is just an issue of simple algebra. So the dimension of the virial current, delta V, is equal to delta phi plus delta U, because we are in a shift multiplet and the dimensions are quantized in terms of delta U. And so I claim that this is equal to d minus 1. So why is this the case? Well, actually, delta U is minus the dimension of the charge, and the charge is obtained by integrating phi over d minus 1 dimensional manifold. So this d minus 1 here is precisely the dimension of the manifold over which you integrate. So the word identity for the shift symmetry tells you that the dimension of delta V is going to be equal to d minus 1.
Excuse me, so here you got a spontaneously broken symmetry for which the charge become ill-defined. Can you reformulate this in terms of just current without using a charge instead?
I can, but okay, it's going to create a few more lines of algebra, but
anyway, there the integral could be over a compact manifold. It doesn't have to be over.
Okay.
yes, it's definitely over a compact manifold what I have in mind. So this is the gist. There are many ways to reformulate this argument. You can write down a word identity without ever talking about the charge. But to me, the main things behind are the existence of the current, the existence of the charge, and the existence of these shift multiplets. So these are the things that give rise to the existence of this operator, vector operator, which has dimension exactly t minus 1 without being conserved. And so that's it. That's more or less resolving the paradox for this dipolar ferromagnet theory, how it manages to be scaled without conformal. What is also interesting is that once we realized this mechanism, we went through the list of other known theories which are interacting and scale without conformal. There are a few of them out there. None of them are as interesting as this dipolar ferromagnet physically, except for one model which describes the theory of fluctuating membranes, which is also an interesting statistical physics model. And it turns out that all of these theories, if you look at them, they all realize this mechanism. They all have a shift symmetry which is spontaneously broken. they all have the shift multiplets and they all have a virial current which is non-renormalized thanks to this mechanism. So it's kind of curious. So I thought that that this is not possible, that the virial current should get renormalized. And it turns out that there is indeed this mechanism which allows it not to be renormalized. So, perhaps this is going to give motivation for other people to look for, once one mechanism has been discovered, maybe there are more mechanisms, so it kind of reopens the Pandora box, and maybe there are more interesting theories out there which could realize scale without conformal invariance. So, I'll stop here.
Yeah, just a technical question. So does Q get an anomalous dimension,
Q gets an anomalous dimension,
even though it's a charge?
because phi gets an anomalous dimension.
Mhm.
So U gets an anomalous dimension opposite to that of phi. You can view it, you can even give it a diagrammatic understanding. So you can kind of write down all the diagrams for the two-point function. U phi mu, you convince yourself that it doesn't get renormalized.
So Q doesn't have eigenvectors.
Q doesn't have eigenvectors. Yeah,
It doesn't have a usual word identity.
it doesn't have a usual word.
The membrane theory you are alluding to, I guess you have the same elasticity and plus a height deformation? Or?
Yes, yeah, you have elastic modulus
plane.
and bending rigidity. So that theory is for free floating membranes. It has a fixed point with non-trivial critical exponents, and theoretically, there's a lot of work on this. These people computed this critical exponent, and recently it was also understood by Katsnetson and Mauri that that theory has scale without conformal. Unfortunately, I don't know of much experimental work on that model. So while it seems to be tough to realize, maybe because it has to be membrane has to be free floating.
Mhm.
It's also not so easy to Monte Carlo simulate. So, but it's an interesting, definitely.
And it has that property for any value of those coefficients, for those moduli.
Because it's in that case, the beautiful thing that it's an attractive fixed point. So you do whatever in the UV, you always fall to the same fixed point. Here, for this model that I considered, you have to tune the temperature. There, it's an attractive fixed point.
Do you expect that there are like a mechanism that would apply to unitary theories? Or you think like unitary plus scaling invariance implies somehow conformal invariance?
Well, I already expected one thing, but it turned out to be wrong. So, well, there was of course some work for unitary theories. So in 2 dimensions we have more or less a theorem that says that scale is conformal, plus scale plus unitarity plus conformal. In 4 dimensions there is an argument. There are 2 papers by Margotsky and collaborators, which give, they little bit fall short of the full proof, not as in 2D, but basically they say that in 4D, the theory which is scale unitary but not conformal is so weird that it's unlikely that it exists. On the other hand, the 3D case, so this 4D case it relies a lot on the form of the effective action when you put the theory in curved space and the existence of anomalies. In 3D, this argument doesn't work. So in fact, in 3D, there is no result. So perhaps in 3D, unitary theories scale without conformal might still exist.
You may have said it, but I missed it. So if you start with a conformal theory in the Wilson-Fisher O3 point, what relevant operator are we talking about when you say that it would flow into this new non-unitary fixed point?
There is no local operator, there's no local operator, so in order to drive the theory in the direction, you have to allow yourself this non-local
It's
deformation.
non-local.
Yeah.
The question is, let's thank Slava